Here's our scanning electron microscope. We're going to start with electrons up here and then apply a voltage. Negative here, positive here, so those negative electrons are going to want to go down. They'll get accelerated, pulled by this positive charge, and then they fly past it, and we have inside here a tin sponge that was made with the tin sponge experiment. When the electrons hit that sponge, they're going to kick out parts of the sample, knock electrons out of the tin atoms, and those electrons that are knocked out, we're going to collect them and use that to make a picture. Over here on the screen, here's just an optical regular photo of our tin sponge, but as we zoom in, this is the electron image that we're starting to see, seeing different places on this whisker of tin that's grown out from the sponge. And we can zoom in and start to see structure that you couldn't tell was there with your eye or even with an optical microscope. We're zoomed in a few hundred times now, and so we're starting to see things that are quite small, almost too small to see with light. You can see this kind of sawtooth structure, and there are these really fine ridges on the whisker as well. This is one of the big advantages of electron microscopy, is that because we can see these really small structures that are too small to see with light, we can learn about how structures grow and form in addition to what their properties are on a large scale. Something else that we can do though is to choose any region that we want to examine and say, if I hit this with really fast electrons, I can get it to make X-rays to produce really energetic light, kind of like the flame test in a chemistry class, just at a higher level of energy. And since each element gives off different specific energies, we can learn what atoms are in each different region of our sample. Maybe the teeth are made of something different than the whisker around them. And for a sense of scale, what are we looking at? Well, I can say, I'm magnified thousands of times. That doesn't mean anything. It's too big of a number. But we could measure one of these, oh dear, and ask how wide is the little tip of this blade. And it's just under 1 micrometer wide. So this is going to be maybe about 5,000 atoms across, this little tip. And that's almost a better number to go by when we're looking at so small of a thing as how many atoms are in it rather than how many times am I magnified.